All right, Yashar, can you hear us?
Yes, yes.
Okay, so let me just say a few words. Okay, so our next speaker is Yashar Komijani from Rutgers University, and he's going to tell us about critical charge fluctuations and superconductivity in magnetic environments. Yashar, take it away.
So thank you for the introduction, and also thank you for giving me the opportunity to tell you about my research. So when I was putting the talk together, I realized that I won't have time to cover superconductivity, but if there will be time, I will comment about it. And I'm also excited that I will be starting a new group at University of Cincinnati, and I will have some postdoc positions available. All right, so let me start by introducing my collaborators. I have been working with Piers Coleman at Rutgers on the theory side, and also with Fermi, Chandra, and Elliot Coney. And on the experimental side, I have been collaborating with the groups of Huiji Yuan and Frank Steglich in Zhejiang University, and also with Satoru Nakatsuchi and Hisao Kobayashi in Japan. All right, so I think I don't need time to tell you a big introduction about the strange metals, but these are a state of matter where characterized by linearity, resistivity, and logarithmic in temperature specific heat coefficients. And they are interesting because they seem to be universal. They were first observed in the optimal doping in cuprate, but also in heavy-fermions, and recently in optical lattices or in twisted bilayer graphene. And here we are more interested in heavy-fermions in this talk, and these are a class of materials which are close to magnetism. They are similar to high-TC superconductors, with the difference that the energy scales are much smaller. And this means that we can use pressure or magnetic field to drive transitions in these systems. So a very good example is this ytterbium rhodium to silicon 2, where with a magnetic field, one can drive a transition between two Fermi liquids. And in between, we have a fan of criticality with the linear in temperature resistivity. This is another example, cerium cobalt indium 5, which is critical in ambient pressure, and the resistivity shows this linear in temperature behavior. The range is not as large as we see in cuprates, but compared to the energy scales of this material, it is a still very large scale. Another signature of this strange metal phase is that typically around this regime, we see Fermi surface reconstructions in the systems. For example, here you see the Hall measurements by Silke Passion on this YRS material, where around this critical magnetic field, the Hall constant jumps and it becomes sharper at low temperatures. And these are famous measurements by Shishido and co-workers on cerium rhodium indium 5, where the magnetic oscillations show a jump at the critical pressure. So meaning that the Fermi surface has changed. They can also extract the effective mass of carriers from the amplitude of the oscillations, and this is shown here, which shows that the effective mass diverges, signaling some sort of a localization. Okay, so the nice thing about Condor lattices is that, or heavy-fermions, is that we know that most of this complicated action is a result of a competition between the Condor and magnetism. Okay, and we can write simple Hamiltonians, and we can access it via some controlled approximations. So let me walk you through this Hamiltonian. On one side, we have a lattice of spins or magnetic moments. These are described by this Heisenberg coupling between the spins. We also have a band of conduction electrons, like free electrons. And these two guys talk to each other via this Condor coupling. Okay, this is the spin of the conduction electrons, and this is the spin of the moment. Now, the magnetism alone and the Condor alone, we understand more or less very well. So as a result of this magnetic coupling, the spins may order, or we may have a spin liquid or some other states. And if we also have one single impurity immersed in a metal, we know that at low temperatures, the metal tends so one electron from the metal tends to form a singlet with this impurity, so that from the perspective of the other electrons, this moment is a screen, and they're just reflected with a phase shift. But the question is that what happens if we have all these three terms on the Hamiltonian? So one way to to gain some insight is to look at this extreme regimes. If I set the JK equal to 0, so I have this lattice of red moments, and these are my conduction electrons. And so these are decoupled from each other. The moments may order, or I may have some VBS or some spin liquid, and the electrons will form a Fermi surface. In the other regime, when JK is large, we know that the spins will be forming this singlet states with the electrons, and they are screened. So typically we have a ferromagnet, which is a Fermi liquid. And what is interesting, from work of Oshikawa and others, we know that this Fermi liquid this Fermi surface contains not only the density of electrons, but also the magnetic moments. Okay. Now, the interesting question is that what happens in between, right? And this goes back to the work of Doniach, and many people have tried to answer these questions using different techniques. But what is really needed is a unified framework which can access both these regimes and also can interpolate in between. Okay, so I would like to advocate a large N theory based on a Schwinger boson representation of the spins. And this has been done to understand the magnetism long ago by Auerbach and Auerbach, and also later by Reed and Sachdev.
Can I ask a quick question? What are you assuming is the nature of the small Fermi surface phase? Are you assuming a broken symmetry or spin liquid or what?
A gapped spin liquid. Typically, that's what I will have.
Sorry?
I will have a
spin liquid.
Yes, yes.
All right, thank you.
All right. So if I have a SU2 spin, I can represent it with a single boson, which is in two states of up and down. But in order to do a large N, we generalize this SU2 to SUN, and also send the size of the spin, or the number of bosons involved, to infinity. And in this limit, if I plug this expression here, I will have a 4 boson term, which can be decoupled two ways. If ferromagnetic couplings would be decoupled, resulting in a hopping of the spinons, and the anti-ferromagnetic coupling will result in a pairing of the spins. Okay, so for example, this delta is the amplitude of having a singlet between the site I and J. So either way, because of these terms, the spinons will delocalize through the lattice. They form a band. They will have some EK diagram shown here. Okay. And typically there is a small gap here. So if the gap remains finite at 0 temperature, we have a gapped spin liquid, and if the gap closes, we will have a Bose-Einstein condensation of the spinons, which is interpreted as magnetization. Okay. So what about the Condor side? So the Conda effect can also be understood using Schwinger bosons. This has been done by Parkola and George. And if I plug this form here, we will see that in the large N limit, the B will tend to contract with a fermion. Okay, but this is a fermionic object, so this has to be decoupled by introducing some Grossmanian variables, which I call holons. Okay, so this interaction vertex is shown here. So this holon is a positively charged and spinless fermion, which mediates interaction between a fermion and a spin. Okay, so for example, electron can recombine with a holon and become a spinon, or a spinon can decay into an electron and a holon. Okay. So this theory not only can capture the normal Condor physics, but also multi-channel Condor physics. And so in the limit of large K, in order to faithfully describe the Fourier screen case, we need to have as many channels as the number of spins. Okay, and in low temperatures, the picture that emerges is that the spinons decay into some electrons into the wires, and they leave behind positively charged holons behind. Okay, and we will have a phase shift by other electrons in the wire. So so this can be captured by the following. So
sorry,
because
can I slow you down a little bit here? Excuse me.
Please.
So now in the large Fermi surface phase,
Yes.
You want to get a large Fermi surface of electrons.
Yes.
But your objects chi and these are not electrons, these are spinless objects. So how is this? How are you going to get the large Fermi surface phase from this approach?
So this interaction can be extracted from a Luttinger-Wirth function, right? And there will be there is a Ward identity which shows that the phase shift that the electrons see is equal to phase shift that the holons divided by n. So basically, by computing the phase shift of the holon, I can extract the phase shift of the electrons. I'll come back to this issue of phase shift versus the Fermi surface in 2 slides. Okay. Is that okay? Can we postpone this question there? So
yeah, sure.
Sorry, a technical question. What is the index A? That's the channel index, or?
Yes, exactly. So I told you, because we have to send this 2s to infinity, right? So therefore, in order to remain fully screened, we need to have also 2s channels, right? Okay, and so this means that I need to add a channel index to my fermions, and when I decouple them, I would have my holon will carry a channel index.
I see.
So as a result of this interaction, the propagator of the holons and the spinons will become dressed by these bubbles. But there will be no dressing for the conduction electrons because they carry 2 index, right? So in this 2 type of diagrams, these guys will remain bare. And this will give me a set of SYK looking integral equations that we can solve self-consistently to follow this evolution from the crossover from the UV to IR. For example, this is the susceptibility that can be extracted from this type of calculation, which shows a crossover from a Curie to a Pauli susceptibility. Okay. So now, how can we combine these 2 together? So remember that we have a 2 layers lattice, so a lattice of moments in red and a lattice of conduction electrons in blue. They are coupled together. It turns out that all we need to do is to modify the propagator of the spinons to have a kinetic term coming from the magnetism and a Steph energy which comes from the Conda effect. Okay. And this there's some connections to the SYK model and also to the DMFT. But computationally, this is still difficult to do. And a good starting point would be to, as a first approximation, to discard the momentum dependence of the Steph energy. And this is what people usually do in single-site DMFT. So if I replace this with a momentum independence of energy, so it turns out that this is equivalent to a Condor lattice, where each spin is coupled to its own conduction mass. Right? So admittedly, this is not sophisticated enough to capture all this complexity that we see in the materials or in the systems, but I would argue that this is a good starting point because it captures competition between magnetism and Condor. All right, so let me show you 2 examples. These 2 examples will be both 1D Condor lattices, and one case will be ferromagnetic and one case anti-ferromagnetic. Okay, and either way, if the Condor coupling is dominant, each moment will be screened by its own wire, and so I will have some Condor singlet here, and the ground asset would be some product of this Condor singlets, right? So here the coupling between the Heisenberg coupling between the spins is ferromagnetic. So if that one is dominant, I will have a 1D ferromagnet, which actually orders at 0 temperature, and the ground asset is again a product state. So this plot shows, for example, this magnetization as a function of the Doniach parameter. So when Condor is dominant, the magnetization is 0, and then at some point it gradually takes off. And on the right, you can see the phase shift that the electrons would experience from the here. So it's pi in the Condor phase, and then it gradually goes down. And so I think so as Subir pointed out, so this is because of this geometry, we cannot really define a Fermi surface. But this phase shift is some sort of or proxy to a Fermi surface volume. So we loosely interpret this as a large Fermi surface and a gradual decrease into the ordered phase. And this is the phase diagram extracted from the susceptibility, and you can see that there is this local Fermi liquid phase, and this is the 1D ferromagnet, and there is this quantum critical regime in between. What is interesting is that the Condor temperature gradually goes down to 0. And so close to the quantum critical point, the Condor is weak because the Condor temperature is weak. Magnetization is also weak. And so I would argue that in this case, there is no active competition between Condor and magnetism. Okay. Now let's move to the, is there any question about this part? I would move to the second example. Okay, so the second example is when I have anti-ferromagnetic coupling between the spins. Okay, and in this case, when the magnetic coupling is dominant, I have a gap spin liquid, a short range U1 spin liquid. It's very much like a halting phase of a spin 1 spin chain. So the transition will be between a local Fermi liquid and a spin liquid. And here you can see the phase shift as a function of the Donier parameter, and it jumps 100% from pi to 0, and it becomes sharper at low temperatures. So again, loosely, we consider this as some sort of a jump in the Fermi surface, and this would be our Condor breakdown transition. And this is the entropy, which shows the collapse of 2 energy scales from both sides. And there is a residual entropy at a low temperature, as you can see here. All right, so here we have a transition, a Condor breakdown transition between a spin liquid and a Fermi liquid. And we have some sort of a Fermi surface reconstruction at the quantum critical point. And I like to argue that when the system is undergoing this Fermi surface reconstruction, adding or removing a charge does not cost much. So therefore, I would argue that charge fluctuations must be soft at this point. And this naive thought turns out to be actually correct, because this is the spectral function of the holons as a function of frequency and the Donier parameter. They are very incoherent, but most of the weight is concentrated on this mode, which comes down and crosses 0 frequency or chemical potential here and goes down. And remember that this is a fermionic mode. So when the fermions are occupied, when the holons are occupied, we have a large Fermi surface, and when they are empty, we have a small Fermi surface. And at the critical point, the holons are critical. Any question until here? All right. Since the holons are critical and they are charged, it can be shown that they do contribute to some to the charge fluctuations. If we compute the charge susceptibility of the conduction electrons, they contribute, the holons contribute, and in fact we get a divergent charge susceptibility at the quantum critical point. Okay, so in this case, so this is transition between the Fermi liquid going through the critical point to the spin liquid, and right here is 1/T. And this sort of critical charge fluctuations at the Condor breakdown has been seen in pseudo-gap Anderson impurity systems, but never on a Condor lattice before. Now, in this case, the holons are local. They are located at this position of the impurities, and they do not move around. But if somehow we could imagine that these holons could diffuse around incoherently, then the conductivity of the system would come from Einstein formula, like a D diffusion constant times the charge susceptibility. And if D is constant, then I would get a Curie conductivity or a linear T resistivity. this is just pure speculation. Of course, I cannot compute the D in the system, and they are not even moving here. But it just gives some intuition that probably this charge susceptibility is tied to the linear T conductivity, linear T resistivity. Okay, so can this charge mode be seen in an actual experiment? No, since the charge is fluctuating, if somehow we could bring a two-level system close to this fluctuating charge, it could be possible that maybe we could probe it. For example, imagine a nuclear transition, and imagine that this nuclear transition is hyperfine coupled to this charge. Then the energy of the excited state is fluctuating together with the charge, and therefore, if I do a spectroscopy on this nuclear transition, I will not see a single peak, but I will see rather a two-peak structure. Okay, and this basically this idea has been tried recently on a different heavy fermion system. This is a beta ytterbium aluminum bore 4. It's also made of it's made of 1D chains of ytterbium magnetic moments, and the Musmira spectroscopy shows a dip. This is the nuclear transition, and this dip is supposed to get sharper at lower temperatures, but instead it remains broad, and it even maybe shows some sign of splitting, right? And so this looks a little bit similar to here. So we are speculating that maybe this is actually connected to this holons in the critical regime. So this material is critical at ambient pressure. You just cool it down and it's critical, and this is where this measurement has been done. All right. Any question so far? So I'd like to change gear a little bit and switch to another heavy fermion. This is cerium rhodium 6 germanium 4. It's a ferromagnetic heavy fermion. And the main players are the cerium atoms in red, which are located in 1D chains, which run along the C-axis. And these chains themselves, they are located in a triangular lattice, and they are weakly coupled to each other. All right. So, recently, in this work, they have studied this material, and from the resistivity, specific heat, and susceptibility, they could extract a phase diagram shown here as a function of pressure, and this is the temperature. So we have two phases: a ferromagnetic phase and a Fermi liquid phase, and the energy scale associated with these two phases collapse at the critical pressure. So most of the quantum critical systems that we know, at least in heavy fermions, they are anti-ferromagnetic, and there are few ferromagnetic systems, but they are usually disordered, or the tuning parameter is a disorder. And it turns out that this is the first stoichiometric quantum critical ferromagnet. And moreover, right at the critical point, the resistivity shows this linear temperature dependence, and the specific heat shows this logarithmic temperature dependence. All right, so we can try to use the Schwinger boson machinery to also model this system. We model it with a 3D lattice of moments, some sort of so they are located on a weakly coupled chains. And again, each moment has its own conduction path. And this model does a relatively good job in capturing the susceptibility. And you can see that for example, in the Fermi liquid case, we get this Pauli susceptibility. And then as we tune to the ferromagnetic system, ferromagnetic phase, we pass through this quantum critical point. And also the specific heat, we can again get the same crossover. And this time we also get a logarithmic in temperature, specific heat coefficient. But can we say anything about the linear T resistivity? Right? And no, I mean, of course, this is a major open question, but I mean, based on these two examples that I showed you before, somehow I would like to associate the strange matter phase to some reconstruction of the Fermi surface, and therefore also some critical charge fluctuations. And I showed you that in 1D ferromagnet, there is no jump in the Fermi surface, there is no critical charge fluctuation, but in the anti-ferromagnetic case, we do have it. So it is somewhat puzzling why this ferromagnet shows any linear T-resistivity based on that line of thought. Right? And to resolve this puzzle, we have to notice that the system has some magnetic anisotropy. This is the susceptibility measured in the system. And if you measure the susceptibility in plane susceptibility, if the magnetic field is in the AB plane, the susceptibility is much larger than it is along the C-axis. Okay. Also, when the system orders, the moments are oriented in the plane, AB plane. Right. So what does this mean? We can get insight with a simple two spin problem. Right? So if you have a ferromagnetic coupling between two spins, of course they can orient in any direction. They could be up or right. I mean, here I have chosen to expand it in the Z quantization basis, but they could orient any direction. Now, if you have some magnetic anisotropy, it turns out that there will be some splitting between the M equal to 0 triplet and M equal to ±1. In other words, these terms are energetically penalized by this term. Okay. And we are left over, so this is a projection which leaves us with the M equal to 0 triplet. And this is an entangled state as much as a singlet. So therefore, a correct picture of this order phase in the ferromagnet might be that it's not just a product state of the spins, but it might be that it's a superposition of all coverings of triplet. And this is a state which we call it the triplet resonating valence bond states. Now, I think it's a question that we should ask is that would such a state show any sign of long-range order? And I have to remind you of this work by Roderick Mosner and coworkers, where they tried in the anti-ferromagnetic context, they tried a state made of short-range singlets on a cubic lattice. And they showed that in the limit of large system size, so when this 1 over L goes to 0, there will be a finite intercept for the staggered magnetization. So even a short-range singlet covering can show long-range order. And we can borrow the result by comparing these two states together. You can see that the only difference is that we need to go every second side on this bipartite lattice and add a sign for the spin. And with this sign convention, sign change, their singlet coverings becomes M equal to 0 triplet coverings, and the staggered magnetization becomes a uniform magnetization. So the picture that emerges for this phase diagram is that the order phase here is not a simple product state, but rather contains this triplet states, which may also be even resonating. And on the other side, in the Fermi liquid side, we of course these spinons have donated their electrons, and we are left with these positively charged holons and a larger Fermi surface. And in between, we have this soup of dangling bonds and everything fluctuating, right? Which is a mystery. We don't know much about it, and this would be responsible for this strange metal phase. And this is not just cartoons. We can go back to your Schwinger boson solver and add some easy plane anisotropy to the system, and we see that the phase shift will not evolve continuously anymore, but it will show a small jump, and the size of the jump is related to the amount of the anisotropy that is included. And so this is high temperature, and then blue would be the low temperature. And associated with that, there will be some critical charge fluctuations. So in this case, it has a different exponent, but it exists at the quantum critical point. So this brings me to my conclusion. So I have a picture, but this picture is not, it's completely backed with my calculation. So the picture is that on the small Fermi surface side, we have this valence bonds or resonating valence bonds in the systems. And as these bonds snap to make singlets with the conduction electrons, we have a jump in the Fermi surface. So essentially, the jump in the entanglement, the patterns of entanglement is associated with a jump in the Fermi surface. And this is accompanied by a fluctuation in the charge susceptibility, or a divergence of the charge susceptibility. So I also showed you that even a ferromagnet can have this kind of bonds, and it can also have a jump in the Fermi surface. Right? And I did not cover superconductivity, but basically similar. I mean, this is the central idea is that if we have a RVB liquid, if we dope it, we get a superconductor, and this triplet RVB systems also, if we dope them, we get a triplet superconductor, and this kind of physics also shows up in iron-based superconductors, where the resonating triplet is actually resonating between different orbitals of the same atom. Okay, so on the right conditions, they can go out and form a triplet superconductor. And with this, I would like to thank you for your attention.
Thank you very much, Yashar. Now we have a few minutes for questions.
Actually, can you go back to your the two models you talked about, the calculation you had? I don't think yeah, could you just remind us what the model was? Okay, maybe that is the slide. So this is on every site you have an SUN spin, is that right?
That's right.
In this particular case, you have like a ferromagnetic coupling.
That's right.
And how did you solve this? Where did you get this phase diagram and these order parameters?
So let's go back to. Basically, I have the main players in my calculation are the electrons, right? Which remain bare. They are just 1/tau Green's function, right? These are spin-ons, and these are the holons, right? So the spin-ons get dressed by this bubble. So these are holons, and these are electrons. So basically, coming from that vertex, and the holons also get dressed by this bubble, right? So these are the self energies. Now, in the case of holons, the only free part of the Green's function is 1/j, okay, here. And in the case of spin-ons, I also have to include the magnetism, right? And the magnetism, basically this free part of this kinetic term, and this will appear in the Green's function here. Right. So, however, I have to solve everything self-consistently. I have also a Lagrange multiplier that imposes the constraint softly. So I have to adjust that constraint, adjust that Lagrange multiplier to satisfy the constraint, and also update this mean field variables t and delta based on the phase diagram. So, for example, actually, you can see here that T is the hopping of the spinels, right? So this is a transition between T equal to 0 and finite T, right? So just this mean field parameter depends on where you are in the phase diagram.
So did you throw away the Q dependence? Is that what you said when you did the self-consistency?
Exactly. So I don't have a Q dependence for it, which basically means instead of the normal Condor lattice, I am considering this kind of Condor lattices.
Mm-hmm. Okay. So now if you just go to the phase diagram that you found for the ferromagnetic case,
yes.
This phase diagram, is it compatible with Luttinger's theorem? If I had, if I were to interpret this as a phase diagram of a ferromagnetically coupled spin system with Condor physics, is it, you have a large Fermi surface and then you begin to get magnetism and, yeah.
Right. So here basically so if you so there is a difference between the ferromagnetism and anti-ferromagnetism. In the ferromagnetic case, the Condor coupling does not normalize to 0 in the magnetic side, so it remains finite, and therefore it means that the magnons are dissipated by the conduction electrons. Whereas in the anti-ferromagnet, because of the gap that is here, the Condor coupling normalizes to 0, and therefore it's different, right?
So in the previous slide, the ferromagnetic metal that you had is some exotic phase. It's not just spins being. I can't just think of it as some renormalized Fermi surface which is spin split.
Sorry, renormalized Fermi surface with
some
no. I think it's not.
Can I interject here if you don't mind? So I think in this picture, if I understand right, and I've talked to Yashar about this earlier, you're considering a model where each spin is coupled to an independent infinite Luttinger liquid. That's the model you're solving, right?
Exactly.
Is that correct?
That's right. Exactly.
I mean, there's the picture. Sorry.
Do you want to switch off your video, Subir? Maybe the audio will be better than, I don't know.
I think Subir disconnected.
Yeah, I think, it's back.
So Ashwin, I don't know if I answered your question. This is not a spin polarized. It's not a spin polarized Fermi surface. So however, I suspect that it's not very different either. I suspect that this transition can be captured by some sort of a Hertzsprung theory, whereas the anti-ferromagnetic case cannot be captured. Because everything is continuous, and it's just electrons just add dissipations to the magnets here.
To the order parameter, the ferromagnetic order parameter, you mean?
Yeah. So Hertzsprung theory of this transition would be in terms of susceptibility of the magnons, right? And there would be some electronic dissipation of it, right? by the Condor coupling. And I think that theory would capture this transition. So I suspect that this is actually within the HMM Hertzsprung universality, which is some sort of a Wilson-Fischer explain.
So maybe Subir had a comment on that, but I don't know if his audio is back up, which I don't see. So maybe till he gets back, can we quickly talk about the second slide, the anti-ferromagnetic coupling? So what you call a U1 spin liquid is what? It's some mean field state of the Schwinger bosons where
that's right.
Pair
that
them.
I have a gap in the. It's like a p-wave pairing of the Schwinger bosons, and I have a gap, finite gap at 0 temperature.
So this is not. This is the fundamental of SUN at every site, or did you stagger them or something? Or?
It's a symmetric representation of SUN. So basically, I showed you. So I have such a term, right?
Mm-hmm.
And they are and the gap remains finite. So I think this is the easiest way
Singlet
to.
between lines. Mm-hmm. I see. So you seem to have a fundamental and an anti-fundamental on the neighboring sides.
Absolutely,
right?
absolutely,
Yeah,
exactly.
Mm-hmm.
So within read and such stuff, that would be
Mm-hmm.
the picture that you just described, and I think the picture is that each one splits to 2, and without breaking any translational invariance, I have a gapless spin liquid.
I mean, that's in the mean field theory. You expect fluctuations to give you some valence bond order or something like that, right? At the end of the day.
No, it's gapped, so I would expect it to be protected.
Well, but you have U1 gauge fluctuations, so that will eventually confine the spin liquid, and in the 2-dimensional case, the analogous thing gives you a valence bond solid, right? Something that breaks translation symmetry.
Oh, for fermions it does. For bosons, I don't think so.
Well, if you, not in the mean field theory, but if you include the fluctuations about the mean field theory, those fluctuations eventually confine.
I think so.
And it depends on the dimensionality, of course.
Right.
But if you're in 2 dimensions, and of course this is 1 dimension, so you don't expect to get a spin liquid, a gap spin liquid, right?
Do you think they would break the translation invariance in 1D?
Right.
I mean, they could do it, right? It's not. It wouldn't be a problem.
Right.
But you mentioned something about the p-wave pairing here. Doesn't that give you like a Chern-Simons term, which eventually gives you deconfinement?
This is 1D. He's doing it in 1D.
Oh, 1D?
Yeah. 1 plus 1, yeah.
And it's p-wave pairing of bosons. So.
Oh, okay.
Yeah.
Yeah. Right.
Yeah, I don't know if you know any work that has studied the role of this gauge field here. I would be very curious.
Well, it's read and such thing, actually. It's one of the read and such thing. Yeah, one of them. Not sure which one you're referring to. Yeah, we can talk later, maybe offline.
Okay, then if there's no other question, let's thank both speakers, and thank you everyone for joining us today. So as you may have noticed in the emails, from now on we'll have weekly meetings, and we'll see you all next week. And thanks again.
Thank you.